Hello, everybody. This is Dr. Eldek, and today I will talk about the fifth chapter in the semiconductor, which is talking about the biasing methods of the transistor, the BJT, bipolar junction transistor. In the previous chapter, we had one method, which is a common emitter, if you remember. But we noticed that this method is unstable. So we try to study other methods of biasing so that we have a forward bias in the emitter side and reverse bias in the collector side, but at the same time we need it to be stable. It's not a function of beta, because beta is varying with the temperature. So when you run, you have current in the transistor, usually we have heat, and when we have heat, beta is increasing, and we have the current IC is a function of beta. It's IP time beta. So this makes the design that you are doing. If you are designing amplifier, for example, make it unstable. You need to design amplifier, for example, to give you 10 times. For example, I need to amplify 10 times. I don't need it to design. I don't need to design something for 10, and after a while it become 12 or 20 or 30 or whatever. So the first method here is called two supply emitter bias, where we have a voltage, positive voltage connected to the collector and negative voltage connected to the emitter, positive VCC and negative VEE. Okay, and the base is connected to the ground, as you can see here. Okay, so let us see if we have a problem like this, how can we solve it? Okay, so according to this, usually we need to solve any problem. What you need to do is to plot IC versus VCE, where plot the load line and calculate IC and VCE. Okay, so how can we calculate the voltage and current in this circuit here? To calculate the current in this circuit, you need to use this loop, this PE loop here, this one. So imagine if this one is negative VEE, then this one will be positive, of course. So as if you have a source here that has a negative here and positive here. Okay, so in this case, this voltage is applied on this loop. So it will be dropped on RB in this part here and on RE. Then you can simply say that VEE equal what? Equal this voltage, which is IB times RB, plus this voltage, which is 0.7 volt, plus this voltage, which is IE, or approximately it is IC times RE. Okay, IC times RE. Then now you have a function of what? Of IC, which is a current here, that this is the required one, and IP, which is not required, but I know that IP equal IC divided by beta. So now I can convert it to one equation in one unknown. One equation, one unknown, which is IC. So once I do that, I will find IC. Okay, and then next I will try to work on the second loop, this one here. You have a voltage VCC in this side, and this side negative VE. So as if you have a source here that is equivalent to VCC plus VE. So positive side is VCC, negative side is negative VE. So in this case, the difference is VCC plus VE. So this total voltage is applied on what? On one resistor, second resistor, and VCE. I want to find this VCE. Then this VCE equal what? Between these 2 points equal this VCC plus VE minus the voltage here minus the voltage here. The voltage on RC is IC times RC. I know IC. And the voltage across RE is approximately IC times RE. Then in this case, I can calculate VC. Okay, so you can calculate it like this. This is the equation for VCE. And this is the equation to calculate IC from the first loop, as I explained. So let us see here, what does the load line look like? If this is the equation, here's the equation. Okay, so the load line will be very easy. If VCE is 0, Then IC equal what? IC equal this voltage here, VEE plus VCC divided by these two resistors. So here is the saturation current, where this point here, when VCE equals 0. If IC equals 0, I want to find this point. Then in this case, if this IC equals 0, then VCE equal VCC plus VE. Then here it is. This is the cutoff voltage, VCC plus VEE. Then you draw this line. Then you know that the operating point is on this line, anywhere here. Then you follow the steps, okay, to find the current IC and the voltage VCE. To solve it, you solve it using these two steps. First, from the left loop, this loop here, the PE loop, okay, then this VEE equals this voltage plus this voltage plus this voltage. Then you can calculate the current IC, okay, using this equation. IC equal VEE minus the voltage here is 0.7 volt or VPE, 0.7 volt, divided by the total resistance here, RP, and this RE, and one of them is divided by beta because the current is different. The current here is IP, which is IC divided by beta, and the current here is IC. So this is the equation that you will use to find the current IC. Then after that, you go to the second loop, which is this loop here, okay, as if you have a source here, that is VCC plus VE between these 2 points, this point and the other point here. So this voltage equal what? Equal this VCE plus the voltage across this resistor plus the voltage across this resistor, as I explained before. Okay, so in this case, VCE equal what? Equal the voltage, the total voltage, VCC plus VE minus the current IC time RC plus RE. So this will be the equation to calculate VCE. So now if we want to solve a problem, we have this one is 100, for example, beta equal 100 volt or 100. And we have this circuit, okay, this one here. And we want to calculate VCE and IC and draw the load line. Let us draw the load line first. We have this equation, okay, this equation. So when to define this point is equal to what? VCC plus VE, as I explained before. So it will be 10 and 20, that's 30 volt. This point will be what? Will be VCC plus VE, which is 30, divided by the total resistance here, RC and RE, 3.3 and 2.7, which is 6K. So 30 divided by 6K will be 5 milliampere. Now, next point is to use this loop to calculate the current IC, to calculate the current IC, then which will be will give you this equation here. Then IC equal VE, which is 10 volt, minus VBE, which is 0.7, 10 minus 0.7, divided by RE is 2.7 kilo ohm, plus RB is 5.1 kilo ohm, divided by beta, okay, which is 100. This will give us 3.38 milliampere. Then we use this value in this equation, okay, here, plug it in IC, put it on IC, to calculate VCE. Then VCE equal what? Equal VCC plus VE, which is 30 volt, minus this current, 3.38, time RC plus RE, which is 3.3 plus 2.7, that's 6K. Then this will give me 9.716 volt. So this is the operating point of this transistor here. If I want to check the stability, then in this case, let us assume that beta, for example, is 200. I believe this is the next slide. Yes. Okay, but let's do it here. If beta is 200, what will happen? Let us see the numbers and compare it with these right numbers here, the right numbers that we have. So beta is changing from 100 to 200. Big change, 100%. Okay. So now what will happen to IC and VCE? Let us see. We use a calculator. And of course, the load line will be the same. There's no difference. 5 milli and 30 volt, because this is not a function of beta. IC equal what? IC equal 30, 10 volt, sorry, 10 volt VE minus 0.7, 9.3 divided by, open bracket here, RE, which is 2.7 K, plus RP, which is 5.1 divided by beta, which is 200. Beta now is 200. Okay, let's close the bracket and then hit equal. Then this is a current 3.41 milliampere. Okay, so you see the difference now. This is 3.38, and when it is 200, it will be 3.41 milliampere. Okay, now what will happen if for the voltage? Let us see. Now VCE equal what? Equal this 30 volt minus IC. Sorry, excuse me. So VCE equal VCEC plus VE, which is 30 volt, minus this current here, time RC plus RE. So multiply this current here time 3.3 plus 2.7, which is 6. So multiply times 6. Okay, here it is. So 20.47. Okay, then they give it negative sign and add 30 volt equal 9.526. So you see here the difference is not huge. There's no big difference. So when you change beta from 100 to 200, all what happened that this one will be almost 3.4 milliampere, and the voltage VCE is 9.52 or 3 here volt. And I believe that this is the same answer here. So when beta equal to 200, this is the answer, 3.41. And the voltage here will be 9.52 compared to what? 9.7 when it is 100. If you remember the previous example, when in the common emitter, there was a big difference between beta equal 100 and beta equal 200. It's almost double. Okay, so here this proves that this biasing system is very, very stable. But of course, the main problem here is what? I believe when you look at it, it is that you have two sources. You must have two sources. Okay, when you add a DC source, it's a cost. You need to reduce the cost. So it is stable, but it has some cost. That's why we can use this system here of biasing. So we have one source only, and we use this R1 and R2 as a voltage divider to provide voltage to the base. So you have voltage here, and you have voltage to the base through this resistor here. Okay. So this is second one, and I believe that is the advantage is very clear that this has only one source.